Get started. My name is Jake Luciani, and this is Carl Yeksigian. We both work at BlueMountain Capital. I'm a Apache Cassandra committer, and we are going to talk to you about how we are using Cassandra to build our TimeSeries database. Before we begin, though, I came up with a joke about Cassandra, and I couldn't not share it. So my joke is, what did the one Cassandra node say to the other Cassandra node after the network split? Can I get a hint? All right. No, okay. So we're just going to go quickly over our use cases and architecture, and I'm going to quickly pass it over to Carl, which is going to take a deep dive into how we've tuned our Cassandra cluster and how we've dealt with certain problems, specifically compaction. So the talk is about time is money. There's sort of two aspects there, right? You know, time is money in terms of latency, and time is money because we have a time series database. So the main idea that we wanted to start with is, describe our problem. Our problem is we have a compute cluster of 1,000 nodes, which are constantly running calculations off of real-time market data. So it basically reads and writes as fast as it possibly can. And all those reads have to be consistent across all readers. We also have a UI so that our team can basically run ad hoc queries, and everything has to run quickly. Oh, and we have multiple data centers. So it's a really hard problem to handle. It's very rewrite intensive, and Cassandra is really the only option for us. So time series intro, I'm sure everyone's seen stock prices. This is the simplest example, the change of price over time. But if you think about it, most things are time series. And for databases like Cassandra, it does really well at dealing with time ordered data. So, in terms of a time series, normally when you're querying it, you basically have two types of queries. The first one is just a time series query where you have a start and end, and you're basically saying, give me a point for each minute. And the other one is a cross-section query, which is the idea of, I have a fund or I have a portfolio, and it's broken up across all these different instruments, and I need to query all of them for a slice of time. And the reason why we keep historical time is because, if you're running a calculation and you want to look at, why did I get this number as of last week, you need to always have the same exact data. So we never update data, we never overwrite data, we're always adding on to the end. Our cross-section data is random, so when you think about searching across any given fund or any given portfolio, you can't really partition that problem because you're never going to know what all possible combinations of that data is. So it's difficult to do, which is why you need something which can scale horizontally. So you kind of have to fan out to get that data. And we also support this thing called bitemporality, which is there's two dimensions of time. There's the time of which something happened and the time in which you learned about it. So say, for example, if you're fixing a bad data point after 2 weeks of it being in the system, you want to be able to go back and run something with the old data point and the new data point. So our system optimizes for time series. And we are using Cassandra 1.2 and CQL3. With CQL3, it makes it pretty straightforward to define this type of table. We've simplified things a lot here, but the main table looks something like this, where you kind of have a identifier, you have a type, for example, price. You have sort of time for the as of. You have time for your knowledge time, which is that 2 dimensions of time, and then you have your value blob. And if you look, we're using the compact storage, which is really like the old style composite columns. And by using that, you can sort of order things. So things are naturally ordered first by identifier. Well, you have to send in the identifier, but then it's ordered by the property, the as of time, the knowledge time. and so on. And the clustering ordered makes it so that you're always looking in a descending. So it's from now going backwards. So to do something like a time series query, it's very simple. You can just do select star from TS data with the ID and this property and the as of time between this and this, and you'll get each knowledge time. And for cross sections, it's similar. You give it a specific point in time. You give it a knowledge time cutoff, where the last point before, this knowledge time, and you get it for limit 1, and you just run this in parallel, right? So you send all these off in parallel into the cluster. So what we built is, none of our clients talk directly to Cassandra. We've built a thrift service on top of it, and we're using the, Cassandra has this thing called the FAT client, and what it allows you to do is sort of act like a Cassandra node without being responsible for any data. If you look in the examples directory, there's a example of this. So what it allows us to do is cut down on the amount of serialization. So our thrift service is sort of running Cassandra internally, but not dealing with any data. It can just use the storage proxy directly. So it can use the same internal protocol that Cassandra uses to talk node to node. This makes it simple for us so we don't have to worry about connection pooling or token identification or dynamic snitch or any of that stuff. It's all built in because it's running the same code as what's running in Cassandra. And what we're doing is we're passing the CQL through that layer. So our applications talk to our service, which is called Olympus. Now, the other thing is we don't just deal with price data. There's lots of different financial data. There's reference data. There's also sort of, when you're running models, you sort of want to track the metadata about your model over time. So that information needs to be stored. So we use thrift structures, and this is similar to Google using protocol buffers to kind of keep things on disk. And by using the thrift union type, we can easily sort of reflect on what type of data we're pulling back. So so our users will create a thrift structure. They'll add it to this union, and they'll be able to read and write data in and out. We don't really have to know what's going on. And then this is just a screenshot of what our UI looks like for the ad hoc queries. I figured I'd throw it in there. And I'm going to transition to Carl.
OK. So that's the easy part. That's our data model. So now I'm going to talk about how we actually scale this thing to handle all of the reads and writes simultaneously. So first rule about scaling is you don't just throw everything at it and let it run as fast as it can, so you don't just turn it to 11. That was actually Jake's slide, so I'm just going to throw him under the bus for that. So scaling, you got to get fast machines. You have to avoid the GC pauses. You have to tune Cassandra, and you have to prefetch and cache inside of your application. So, but before we get there, you can't fix what you can't measure. So we use Riemann, which is a really great stream-based monitoring system. So you can easily push application and system-level metrics. So Cassandra has a plugin for this. Currently, we push about 6,000 metrics per second into a single Riemann instance. So this is the little snippet of code that's required to actually hook up Riemann into Cassandra. So there's two components to our Riemann setup. One is the dashboard, which shows us the live stats that we currently have, and one is Graphite, which shows us historical stats. So using both of them kind of gives us a good picture of what's wrong now versus how has it been acting in the past. And then Visual VM is a tool for the JVM, which shows you a bunch of information about your JVM. So it shows you what the threads have been working on, what's going on with your GC. It also has like JBeans plugin. So it's got all sorts of great tools for it. So getting the right hardware is really important. For us, we got SSDs for all of our hot data, and we're going to get spinning disks for all of our cold data. We use the JBOD configuration. That way we can use as many disks as possible. We don't have to go through the RAID controller. We don't have to do software RAID. You want to get as many cores as possible. So we have machines that have 16 cores. We're looking to get machines that have like 32 cores in the future. We currently have a 10 gig network, and we actually use bonded network cards, so we get 20 gigs on a single machine. And then in order to actually take advantage of a 10 gig network, you have to use jumbo frames. So JBOD really helped us out. We actually had multiple simultaneous SSD failures because of bad firmware, and JBOD allowed us to swap out those SSDs and continue running the cluster. So our end users didn't actually notice that these machines were down, even though we were taking out SSDs. So actually, configuring Cassandra is another big part of making your application go quickly. So there's 3 components that we went through. One was configuration of Cassandra. I'm not going to talk about it at this one because we only have like 5 more minutes. But we have a slideshow that we did in New York that has all of the configuration that we did. The next thing is compaction. So that's actually a big part of the time that the CPU time that we spend. And then compression. So we actually switched to a faster compression algorithm called LZ4. So we use leveled compaction. The good part about leveled is that it limits the number of SS tables that you have to read. So even though you have all of these levels, you know exactly which SS tables will actually contain the data that you're reading. So it puts an upper bound on the number of SS tables that you actually have to read. So we use wide rows, which is why this is actually an issue. But under high write load, all of these SS tables, as the mem tables get full, they get flushed out to disk. So in your level 0, which is completely random data, you have to read every single SS table in order to figure out what data you actually need to respond with. So our original attempt, which is actually included in Cassandra 2.0, is this thing called hybrid compaction. So it was just rolled into regular leveled compaction, and what it does is, in the first level, rather than just doing the regular compactions up to level 1, what it does is it takes a bunch of the SS tables and it does the old size-tiered compaction. So that way you have fewer SS tables that you have to read when you're doing this heavy write load. Now we have a new idea that I'm currently working on. It's called overlapped compaction. And basically what this allows is that instead of taking your level 0 files and combining them with level 1 and then writing all new files into level 1, it just takes your level 0, it does the regular compaction that it would up to level 1, but it doesn't take level 1 files. And at some point, it switches back into this regular mode of taking all of your files at the tier, at the level, and combining it with the level above. But this way, you don't have this bottleneck of, I have to take these files and the files in the next level to do the compaction. So this will allow us to get higher throughput because we'll be able to do more parallel compactions. And then another thing that we're working on is a C-optimized library. So there's actually a lot of time spent on the read path doing comparisons and doing the CRC check for compression. So the composite comparison actually eats a lot of cycles. So CRC check is implemented on the chip for a lot of architectures. So if we can take advantage of that, that'll give us a huge increase in throughput for compressed data. So we're working on actually building a JNI library that will contain a bunch of these native implementations. So right now we have 16 nodes across 2 data centers. So our replication factor is 6, but that's 3 in each data center. So we can lose a node in either data center, or we can lose an entire data center and continue operating. We get 200,000 writes per second at each quorum and 150,000 reads per second at local quorum. So the difference there is that writes have to be acknowledged by both data centers. Reads only have to be acknowledged by the data center that you're in. And we currently store over 30 million time series, and we have over 15 billion data points. And that takes up about 10 terabytes of data on disk. And our read latency for the 50th percentile and the 95th percentile is 1 millisecond and 5 milliseconds. That's at the application layer, apparently. All right, are there any questions? Yep. Can you go up to the question microphone? Thanks.
Yes, I just wonder if you actually benchmark performance with and without Jumbo frames on 10 gig Ethernet, because I'm also curious about this problem.
Yeah, so we did a bunch of benchmarking for our workload, and that's how we came up with the configuration that we did. So we have like a 12 gig heap, we have a 2 gig new gen. So there was a lot of tweaking that we did originally to try to.
I guess my question is specifically about the use of Jumbo frames, and if you were able to measure the performance difference with and without them turned on.
Yeah, we didn't really measure the performance of jumbo frames. It was just like that's our network configuration in order to really utilize the 10 gig network. So without the jumbo frames, you can't actually utilize the whole 10 gig network that you get. So you're back to basically having a 1 gig network.
And another question is whether you noticed any problems with Jumbo frames in terms of, for example, routers and other networking infrastructure outside the Cassandra cluster.
Yeah, we actually had a lot of problems with jumbo frames. Our original structure was that clients would talk to the Cassandra cluster, and there were a lot of packets that would get dropped between them. We would have like some machines that just couldn't talk to the Cassandra cluster. So I don't actually remember how that got resolved, but.
Yeah, the basic thing with jumbo frames is your entire network has to use jumbo frames. Otherwise, it doesn't really work. So that's one of the reasons why we have a separate service, right? So our Cassandra cluster is jumbo framed.
By the way, it is possible to use 10 gigabits without jumbo frames, in my experience, but certainly I'm not.
I mean, just our experience, we had some issues with it, but.
Just open multiple connections and use direct NIO calls.
Okay, thanks.